Okay. Money. So today we have a last lecture. So idea of the today's lecture is that we started with a certain number of hypotheses. Well, I could make it with 6, which together lead you to the wave equation. And then we saw that, in principle, if we relax one of the hypotheses, relax it weakly or strongly, we have some physical effect. I just showed several of them. So in principle, you can associate some effect to each violation of each of them. And the two that we will consider today one was H2, which small oscillations. And another was H6 is long wave approximation. So the first was used to linearize. The second was to keep only the lowest order derivatives. So when we relax this, the first hypothesis, when we say that it's not either the oscillations are not small or not that small, so we want to consider some better model, then we have nonlinear terms. We have to add nonlinear term. And in the second case, when we don't consider very long waves, or either we want to take into account that they are not infinitely long, either they are really not long at all. So when this hypothesis is violated, we have dispersion. And separately, we saw what happens in the first case if you start with a wave. So in the first case, nonlinear. So what does nonlinearity if you start with some wave moving in certain direction, like say in the right, that what happens with time, that depending on the sign of nonlinearity, it will deform the wave to one side to follow in front or to fall backwards, depending on what is the nonlinear coefficient. So this, so its effect is it try to overturn the wave, and the dispersion, what it does. So if you start with the same wave in the beginning, what will happen, it will spread. And it will spread in such a way that it will spread into different harmonics. Each of them will move with different speeds. So essentially, at large time, it will just disappear. So the spreading. So what we do today is we looked at the effect separately, but at the same time, the effect can be both effects can be important together. So today we'll just take them both, combined effect. So what you would expect, so nonlinearity will try to make the wave steeper, but whenever it's steeper, it's more dispersive. It becomes stretched back. So this is getting stretched. Nonlinearity again starts to make it. So somehow they act in directly opposite directions. So the ones try to make it steep, and this try to make it shallow. So what we can expect something interesting that when they put them together, because they act against each other. So now what we will first do is we will consider wave with weak. So both effects we will consider in a weak form. Weak nonlinearity and weak dispersion. So both effects are weak. So we already know what to do with weak nonlinearity. We should take wave equation and add nonlinear term, which we said, which is epsilon u du dx. So this is a no, sorry. So what we did with nonlinearity? With nonlinearity, we took the wave equation and then we know that wave equation solution can be written as a sum of the left-going wave and right-going wave. So we wrote that u xt is a right-going wave plus left-going wave. So then we saw that if all effects are weak, then we can neglect interaction between the left-going wave and right-going wave because they don't spend much time together. Right? So whenever extra nonlinearity appears, then wave can interact with itself nonlinearly. It happens all the time, but interaction between them happens just short time. So then what we did is we just took equation for this UR. Which is also solution to that equation, right? So this any solution of this equation is solution to that equation, but this is only limited to the waves going to the right. And then we can write the same equation, but equation for the left-going wave. Okay, no? So the next step, that's kind of simplifies our life because we will work with lower order differential equation, partial differential equation. So then we found that we have to put the linear nonlinear term, nonlinear correction, so leading order. So leading order. Leading order, nonlinear correction is a term which is proportional to u du dx. Right? This is what you showed because this is a lowest order. So lowest, it's just quadratic because u is small. So if you take cubic, it will be even smaller. So this is quadratic is this lowest order nonlinearity, and we need at least one derivative because we assume that u equal constant should be a solution for any constant. So this is correction. So the equation, corrected equation, will be du. This is for r, right? So this is dt plus for right-going wave dx, and then we add epsilon u equals 0. So this is a right-going wave nonlinear equation. Take into account, assuming that nonlinear term is small, and we just want to take into account the main effect Of course, there is second order term, third order term, and so on, but this is the main. So all others are much smaller than this. Okay, so this is this part. So we saw now dispersion. We did not consider weak dispersion. We considered dispersion in completely general form last time. So now we have to say what is weak dispersion. Weak dispersive correction to a wave equation. So how you derive it? So again, we will stick to the right-going wave. So let's, for the same reasons, we just consider right-going wave. In that order of approximation, it's okay. So whenever you just take this leading order term, you don't need to consider the other approximation, the left-going wave. So that's, we justify it kind of intuitively, but this you can actually derive it mathematically. So we don't do it now. So we still consider right-going wave. So we should add, we must add higher order derivatives terms. Order derivative terms. Right, so that's the whole idea of the dispersion, is that when the wave is very long, so every next higher order derivatives are smaller. If the wave is very long but not extremely, well, but not infinitely long, then the next, so we already have first order derivatives, so we need to put higher order derivatives. So we first guess would be second order derivatives. Right, so already there are all first order derivatives are here, so we can add second order derivative or third order derivative and so on. So first is to show why that second order derivatives are forbidden, and for that let us remember that. Let's remember the two symmetries. One is a parity, another is T symmetries. So one symmetry is x to minus x, so we change direction of the x-axis. Another is t to minus t. Usually this is called parity because in 3 dimensions it maps left hand to the right hand. So if you change coordinates, sign of all coordinates, the left hand become right hand. And this is called time reversal, t minus t. So both symmetries were assumed in the derivation of the wave equation, so we still should keep it. So we say that we will only break this second and sixth hypothesis. We don't break the others. So now here you should be careful because P and T symmetries are symmetries of the full wave equation, but they are not symmetries of the right wave and going wave, left going wave. So you see the question is that whenever you change x to minus x, the right going wave becomes left going wave. Right? And this is exactly what you see. So changing x to minus x, you get minus here. So this has become this equation. And also if you change time, then the right going wave start going backwards and it becomes left going wave. So you change sign here, it gives you minus, so it's just against the same equation. So we don't have P and T symmetries separately for equation of our right going wave, but still what we preserve, what is preserved for right going wave equation is a PT symmetry. Which means that if you change x to minus x together with t to minus t. So if you change x to minus x, left going wave will go to right going wave. But now you change time, it again changes direction again, so it will still go in the right way. So if you change x and t signs, so you get two minuses, and it's still the same equation. So this is how this P and T symmetry for the first equation just translates into the equation for the right-going wave. And since these symmetries are not broken, so we still keep them. So what we should keep is the PT symmetry for this equation. So this is, we should assume that whenever you change sign of T and X, the equations together, the equation should not change. So what you see, when you change T and X together, all terms change the sign to opposite sign, so it cancels. And that means that second order derivatives cannot enter, because second order derivative term will not change the sign. Yeah, so they will not be invariant. So second order derivatives are forbidden. Because it will not be PT symmetric. And actually, that's why second order derivative is in fact a dissipative term. It's a term which is breaking this symmetry. So with dissipation is breaking this symmetry, time reversal symmetry. Okay, so that, but third order derivatives are okay. So third order derivatives are okay. Okay, so it means that third order derivatives are the correct, are the most important dispersive terms that you can put. And but there are many. So you can have third time derivative. You can have second derivative in time 1 in x. You can have 1 in time 2 in x. And you can have all in x. So there are 4 terms that in principle you can add with different coefficients. But now we can use the same trick which shows that these terms to that order of approximation, all these terms are actually the same. Why? Because for weakly dispersive system, so for weakly dispersive system, we need that these terms we can add, but they will be small. So the main terms will still be the ones of the system. So we still will have approximately du dt is approximately minus a du dx, plus more terms, but which will be small corrections. And this means that in this level approximation, for example, d free u dt cube. No, let's start with that. d free u dt d2u du2 dx2 is what? It's let's first take x derivatives and then u derivative, take t derivative. We use this formula, so this is exactly, and then it's approximately minus a d2 x squared du dx. We use this formula, and this is third x derivative. So we see that this term and that term are approximately the same. And then you can do the same for the next second derivative. What you do, you remove t and x and keep just one t derivative. Use the same trick. This gives you one more less, and then this we already did. So it will be minus a by minus a squared etc. So all terms are just equivalent to the last term. So to the linear approximation, we don't need to care about all 4 terms. We just add the last one. So the final form of equation, so we drop of equation for right-going wave. I will drop the index r, no? So it will be what? So we have to add these terms, and we have to add these terms. So we get du dt plus a du dx, then plus epsilon du dx, and then plus this term with some coefficient. Put b, d free u dx free. So that's our equation where we take at the same time non-linear correction, non-linear, and dispersion. Okay, so that's 2 terms. And you see that we derive it just from symmetries, so that means that this is a universal way. This is rather universal equation. So whenever you have a system of whatever origin, physical or the other, from which is where your wave equation is obtained from this hypothesis, by adding the nonlinear effect will have this form, and dispersive effect will have this leading form. So that's why this equation actually appears directly. It's derived in many fields directly from equation of motion, but whenever you derive it from equation of motion, so what the physical meaning will... Very nice. Hã? Ah, mas você funciona, não? Para você. Só que não tem luz. Não. Ok. Funciona ainda? Hã? Okay. So the only physical, really, where the physics or the modeling will come is to define coefficients. We have 3 unknown coefficients. So if you, for example, study the example that we will consider, the waves on the surface of the sea, then the A, epsilon, and B is, to obtain this coefficient, you need to solve really equation of motion for the water. But well, you already from these considerations, you know that a form of the equation will be like this. Okay, good. I can give you another slightly different way how to see that dispersion must have this form. Is the different derivation. Of this term. So how, just to see, to have another point of view. Remember that what we said, that in general the dispersion relation leads to the, so what we did, we had the equation of motion. So it was d2 d squared plus, okay, no. So we had the general dispersion relation had the form the omega squared equal some function of k squared. This is what we did last time. And also we know that it can be it can be expanded in Taylor series so that it's a squared k squared at small k plus larger term. So this is exactly expansion at k equals 0. So when you neglect this term, you get wave equation, no dispersion. So what you can do, if you want to take into account dispersive term, you should take the next term. It's in k squared, so the next term will be k4. So now let's compute omega. So then omega is square root. So we remove ak squared, so it gives you ak root 1 plus c over a squared k squared. And then we expand the square root in Taylor. V1 plus 1/2 of the second term, right? So again, multiply it back. It will be ak plus c over 2a. 1a cancels. And k is k cubed. K cubed. So the weakly, you see that whenever you have weak dispersion, the next term is index for the omega is not k squared again, it's k cubed. So it's strange, no? Today's. So the leading order approximation would be that omega is approximately ak plus c, let's do c over 2a k cubed. So forgetting this correction. And let's see what dispersion relation you get from this dispersive term. So you put in the cubic dispersive term. How we get dispersion relation? We take the solution, which is exponent ik x minus omega t, right? So every derivative in k will give you ik. By exponents will be the same, so we already cancel. So this derivative gives you ik, this derivatives give you a, no, this is I minus I, it's in time, right? So it will give you minus I omega. This is first derivative in time. In x, it will give you ik, so plus a ik. And the cubic derivative gives you ik is 3 times ik, so cube. So that will be dispersion relation. So it will be minus I omega plus I k minus I b k cube equals 0. I cancels. And then we put omega to another side. And get omega equal AK minus BK cube. So just the same expression that we had before. So here what we have B equal minus C over 2A. So that's kind of another way how to see that the next term is that you expand, you take your dispersion relation. You remember that wave, long wave approximation means very small k. So if you want to take into account very weak dispersion, so you just take the next term. And for the derivation, next term is directly described by that equation, by the third derivative. So anyway you go, you come to that equation. So we have an equation which is du dt plus a u dx plus epsilon u dx plus b u dx cube equals 0. Okay, so next change, now we use take change of variables. We will make two changes, two steps changing variables. The first change of variables is the same as we did before. So the unperturbed way, unperturbed equation, so unperturbed solution. So if you take both epsilon 0 and b equals 0, so this will be just wave moving with constant speed a. And this term just lead a weak and slow changes to the shape. So since they are slow and weak, so the first thing what we do, we go to the reference frame which moves together with that wave. So the first we take, instead of x, we take new x variable. Let's see, so I just do this. Yeah. So we take x, first we take new x variable, which is x minus at, right? Without changing time. So we just move together, we go to the reference which move together with a linear wave. So what you do then, so what will change? So change du dt will now be, you see, so you go from variables xt, you go to variables x prime, t, like this. So now we're in these two variables, and if you want to the derivative with respect to original time is the same as derivative with x dx dt plus du dx. When you change variables, you have to use chain rule. So now this is changing variables. So these new variables. So if you want to compute derivative with respect to t here, you take a chain rule with respect to x tilde and then t. And this is minus a. So we get minus a du tilde plus du dt. And the other derivative du dx, or you see it's du dx tilde dx tilde dx, yeah, because it only enters here. And this is 1. So there is no change in the space derivative. So you now, and also in the same way, there is no change in the third derivative as well. You just differentiate it again in x and again in x, so the second and third derivatives do not change. So now we take all of this and put it in the equation. So what you see,
derivada parcial do em relação a t apareceu dos dois lados da equação.
okay, no? Because this is one. But I'm not just not. I'm telling you that I don't use tilde. For t. So what we get is the first term will be this minus a du theta du theta plus a du theta. So we go to the reference frame, it cancels the terms with A. So we have this one term less. So the next, what we do is that we take this x tilde, and I want now remove epsilon b. So there are different ways how to do that, but one of the ways that we will consider is that we take epsilon tilde equal to the cubic root of b, cubic root of b by psi. Psi is our new variable. And also I change u. I take u to be 6 times cubic root of b divided by epsilon. And w will be my new variable. So I don't change time. Time, you see, time you get du dt, it will be dw dt, and you get this perfecta, like 6 cubic roots of b by epsilon. This term plus epsilon, and then it will be w dw dx w dx. So from twice w's you get 2 square of these coefficients. So it will be 6q square, then cubic root of b squared, epsilon squared, and then from x you get this term. It's 1 over cubic root of b. And then the last term will be plus b. This b cancels. And then this term cancels with that term. This term cancels with that term. And it also cancels, so 1 epsilon cancels. So it also cancels with this term, only will keep 6. If you remove 6, it will be just the same, because there is also the denominator. So you end up with the equation which is dw dt plus 6 times 6. We keep 6 because it's convenient. You could do just, you can make a equation with 1 as well. See? Plus And we get this equation where no unknown coefficients at all. It's a completely universal equation. So this equation is called Korteweg-de Vries equation. Korteweg-de Vries. Korteweg of Korteweg Vries equation. You usually seldom write the full names because it's most of the people use abbreviation KdV. This is KdV equation. So it turns out that KdV equation, you obtain KdV equation when you go into the reference frame which moves with the sound speed, and you take into account the small nonlinearity and small dispersion, and the coefficients you just put to 1 and 6 by proper rescaling of the coefficient. Proper rescaling, choosing the proper scale in x variable and proper scale in u variable. That's it. So now all what we now have to solve this equation. This is a very interesting equation. Actually, there is a whole book about how to solve it, because it turned out that you can solve it. It's one of special example of integrable systems. So it means that you can just find the solution explicitly, but through a very non-trivial transformation that relates this equation to the Schrödinger equation. So somehow you get the equation by solving the equation from quantum physics. But what we do, we do something much simpler. Let's take coffee and then solve it. So take a short break. So how to solve? So first of all, we're not going to make a general solution. We will only consider wave solution. So we will look for wave solutions. And specifically, we will look for the solutions W, which is a function of psi and t, which has a form of the traveling wave. So it's with a function which depends only on psi minus vt for some v. So remember that this means that W has some shape and it moves with speed v. So in some sense, what it means, so remember that we're already at the moving frame, and that frame moves with exactly the sound speed. So what we say that actually, whenever you add these two terms, it will still be the wave, but not exactly moving with the speed a, but with some correction v, a plus v. V actually, a plus v multiplied by this, because we rescaled x. Okay, so because if this equation has the wave solution, there is no reason for it to have exactly the speed of the sound speed. It can be just slightly different. Okay, so we take this equation, and we say, so what we can say that, in other words, that W psi t is equal to W capital of eta, where eta is psi minus vt, the running variable. So let's now write, we'll see what this gives you. So the derivative W in time, it will be derivative with respect to eta, right? And then derivative of eta with respect to time. And this derivative is minus v. I'll take prime as derivative with respect to only variable. So then dw dx is the same time as dxc. It's the same thing, so you first differentiate with respect to eta, so it's prime, and then eta with respect to xc will give you 1. And then third derivative, you just keep taking derivative from this expression, and you get third derivative, right? So taking one more derivative in psi, in eta and psi, so it's every time you take derivative in psi, it's the same as taking derivative in eta. So we put it inside that equation. It will give you minus v w prime plus 6 w prime plus w 3 primes equals 0. You can remove one of the, what you can do, you can remove one of the derivatives. So it will be plus 3 w squared like this. See, when you differentiate this with this, you get 6 w prime. So this is derivative with respect to eta, and this should be true at all points. So that means that this expression is constant. So now which constant? So what we want, we want a solution which vanishes as far away. So we want solution which goes to 0. If solution goes to 0, this goes to 0, this goes to 0, this goes to 0. So in that case, constant is 0. So now we have simple equation. So the question is, so I have this equation that this term plus this term plus this term equals 0. So I will put double prime second derivative on the left, and the rest on the right. And the next, what we do is I can write this equation as W double prime equal du capital minus du capital dw, where u of w we define as w cube minus v over 2 w squared. So see, if you differentiate with minus, first you take 3w squared and then plus vw. And this is an equation that you already know, because remember equation for the motion of the particle with potential energy u of x. So you have a direct analogy so you take m equal 1, so it gives the same term. Then here it is a derivative with respect to eta, so it's the same as time here. So this was time derivative, this was eta derivative. And then here we have w, and for the particle you have position. It's just the same equation. So we know how to solve it with this potential. This is one of these exercises that we had. So we need the potential. We need to see what is the potential. Here. So there are two situations. One situation with if v is negative, then the potential function, so that's u as a function of w. In the particle, we use a function of position. So if v is negative, so this is sum of cube plus square. Cube plus square, it gives you this function. So it's 0. You see, it passes through 0, where it has also derivative 0, and also another root is v over 2. So this position, this is v divided by 2. And then we know that if you consider phase space, this is a minimum and maximum. This is fixed point. This is stable fixed point. So there will be these solutions. This is unstable fixed point. Like this. So this is our diagram. So these are all solutions that this system will have. But now the problem is that if W goes to 0 as eta goes to plus minus infinity, that condition that wave goes to 0 at plus minus infinity, we only have the unique solution, which is just 0. Because there is only solution that passing through this point is just 0. So this is case, it means that this is not an interesting case. Not interesting. So that means that we should consider the V positive. And if V is positive, then our potential, this effective potential, this root is on the right. And now it has this shape. And if it has this shape, then the diagram in the phase space, now this is unstable and this is stable. So now the stable equilibrium is here, and this is unstable coming from 0. This is a diagram. And in this case, we do have interesting solution which comes from 0. So there is still the same solution, which is just 0, stays at the same point. But then there is another solution, which is a separatrix. So there is a solution which corresponds to separatrix, and which is 0 at minus infinity and 0 at plus infinity, which is exactly what we need. So this solution you can find explicitly for this system. Just make some exercise in calculus to see the equation. I will show main step, then you can fill it in. So how you find solution? First of all, the finding solution. Let's remember that. So this is a motion of particle with a potential energy. So it conserves energy. So the energy for this equation should be conserved, and energy is W prime squared by 2 plus U W. So it should be conserved. You can just differentiate and see that it's conserved, but we already know. And so the energy, so this is energy. But we can compute this energy. This is energy of the separatrix, so the same energy as this energy at the origin. But at the origin, everything is 0. You see, U is 0 and W prime is 0. So that means that separatrix solution corresponds to equal 0. So we put 0, and then you can express W prime will be equal to this. You put another side, so it will be square root of 2U. plus minus. Then you use expression for u. I'll start with the last term, so because it's O minus. Minus 2 in square root. So I'll start with v term, so it will be v double 4 minus v3. And from that, just removing, putting out the first term, it will be plus minus square root of v. V is positive, so we can take square root. W is, we also know it's positive along the whole solution, so we take square root. So it's and then the square root of 1 minus 2w divided by v. Okay. Then we will write that this is actually dw eta. So we write pull eta. So then the eta we must put there, and the denominator, the right hand side we put in the denominator. So this is plus minus dw, and then the whole stuff in denominator. V, and this square root of v I will keep on the left. Like this. Agree? So the next step is we can integrate it. So we can integrate both sides. And this is the integral in eta. So it will be square root of v eta. There is integration constant, so I put it here. So I can just put both integration constant in here, and then equal to, and how you integrate the left hand side. So in order to integrate this, so what you can do, you take new variable, which is z equal to w over v. So you call this z. And then it will be plus minus integral. So the coefficient will cancel from these two, and this will be just integral dz z square root of 1 minus z. And if you look at the tables, or you just know how to do this, you will see that this is 2 arc cosines hyperbolic arc or hyperbolic cosine of 1 over square root of z. Well, that's last step. You should know how to do. So this is plus minus 2 arc cosine hyperbolic square root of z. So now what you do, you put 2 there. You put, so so then you can express this business as 1 over square root of z will be cosine hyperbolic of square root of v divided by the 2 eta minus eta 0. I don't need to write plus minus because it's the same thing. And finally, I take the minus 1/2 no, I take minus 2 power of both sides. So then you get the final answer. Almost final answer. Get that equal cosine hyperbolic minus 2. And now remember that we use these variables. So we find that W, the difference is just V divided by 2. Of this whole business. And then remember that what was our solution was W taken at psi minus Vt. So we put it there. So that's our final solution. So we found that the shape, there is a very particular shape of the wave which can exist. It's a function which has a form of the cosine hyperbolic minus 2. It very fast exponentially goes to 0 and stays at certain form. So so in other words, for every velocity, we have a wave which has the same shape. It's just wider or taller or shorter, and this is a wave which has a very specific form. Yeah, so that's not any shape. So it would mean that the wave, if we send a wave which initially can have arbitrary shape in the wave equation, but if we add weak nonlinearity and weak dispersion, then after some time, if the wave will propagate with a constant speed, it must have this form. So it will deform, and it will keep deforming until it reaches this form. So this form, so we know that it has to reach. Probably it will emit some other ways to the sides, but it will not. It will never. Can only reach the stationary shape of this form. So this is one of the solutions. So what we can say is that, in principle, there are other solutions for other energy. So this is we obtain the solution for energy equals 0. Energy 0 is our soliton solution. But if you consider negative energy solutions, then you can have, so this is energy equals 0. That's energy, it's not really energy, right? It's just what we call energy through the analogy between the two equations. But when energy is negative, so when energy is negative but still small, so what you have a solution which is so when you write somewhere like here, so you have a solution which is like this, right? So it's close to separatrix, but it's now periodic. So what happens here? It's very slow because velocity is slow. So it goes slowly here and then poof, make a circle. Slowly here, make it circle. So the form of this solution will be close to this shape. So it will kind of make a shape, then it will pass close to 0. and then make the shape close to 0 and so on. And then if E is not anymore, is not small, then you already have, so it's not, and then it's already, if you have consider solutions close to the minimum, then you're close to the sine function. Just oscillate. So that's it. So now I would like to show where do you see these functions, these solutions, and where you see these kind of equations. I think one of the most interesting applications from my point of view is the waves in the sea. So consider the beach. And then you have a water. This is water. And the situation when you see this wave is if the beach is if this you have the depth is changing slowly, then what you have, you can separate the whole region into the 3 pieces. So one piece will be deep water. So your waves are much shorter than the depths. So in that case, remember, we had this is a situation we considered yesterday. So we had the dispersion relation was, I think it was like this. Over K. So this is a strongly dispersive, strong dispersion. So what means that's why far away you don't really see far away in the sea. You don't really see the very specific. Well, we saw that if the ship will come through, it will form that pattern. But if the ship, but after that, if you wait for a longer time, you will see that waves just move chaotically. You don't have any specific pattern forming, just wave come up. So the wave cannot, they cannot be, the stationary wave do not form because dispersion will always break them down, disperse them out. Yeah, so even though they can be, the nonlinearity cannot overcome dispersion. Dispersion is very strong. Also, the next, the other regime is very near the beach. So what you have here is that the wave which comes, its weight, its size become comparable to the depth. So this is strongly nonlinear. Remember, linear means in this case means that the amplitude should be much smaller than the depth. So it's strongly nonlinear, and when it's strongly nonlinear, at this, what happened is that nonlinearity start to break the wave. So this is exactly what happens in that side. The wave breaks. So breaking, wave breaking. Wave breaking process is very complex, but initial phase, the initial inclination we already kept with the Burger's equations. So now in the middle, green. So in the middle between the two, so what we have? We have a shallow water. Which means that we're in a weakly dispersive. And also it's sufficiently deep. It's sufficiently deep so that the wave is actually small. So it's weakly nonlinear. So it's the same height for the wave, which is here can be small compared to the depth. Here it's become large compared to the depth. So here it's just deeper. So in that case, we have both hypotheses. It's both dispersion is weak and nonlinearity is weak. So in this region, we have a Korteweg de Vries equation valid. And exactly in this case, in this region, where you observe these solutions. So somehow, when waves propagate toward the coast, far in the deep ocean, there is no any pattern. But at the moment they enter in the region where the KdV equation is true, they start to form the waves, these solutions, because these solutions are stable. You can show that it's stable. So they start to form these solutions. So they choose one between these solutions. They take the right one. The right one, actually, they take. It's another question issue how they choose. Well, essentially, how they choose, you can compute. Each of the solutions has a certain flux of energy and momentum, and there is a sort of ratio between them. So they choose the solution which will carry just right energy, right momentum. So they will choose specific solution from there. And this is solution that you will see here. So independently of what happens chaotically here, in the region of the KdV, they will choose that pattern, and you often see that there is a wave which is actually very close to cosine hyperbolic -2, and then almost nothing happens. Another wave, almost nothing happens. Another wave. So this is often you can see. So that kind of the wave separated by almost horizontal section, waves more horizontal section. So what I didn't say, so this is called soliton. Soliton is because it's solitary wave, just one wave. And these kind of solutions, they are called cnoidal waves. How it's spelled. So this is a region of KdV. You form the periodic pattern with a solution which look like solitons. They spread out. And then when they come to the beach, it becomes strongly nonlinear because now the nonlinearity is dominant, and they fall. So that's three different effects. So strong dissipation in deep sea does not allow you to form any pattern. When it becomes shallow but still weakly nonlinear, you have very well-defined periodic waves which form, and then you come to the beach and they fall because nonlinearity becomes strong. I'll probably show the picture. It's for you to remember. But what I recommend, you go who lives in Rio de Janeiro, you go to the Arpoador beach. There is a rock where you can just, from a side, see exactly this all forming. So it's just way around, no? So the beach is on the right. And you will see that in deep sea, there's just waves coming and going. There is no periodic wave coming from this deep sea. Just something happens there. And then suddenly in the certain region where it's already, it's still deep so that the wave is short, but the depth is small compared to the wavelength. So it's weakly dispersive. So in that region, you suddenly get very clear pattern forming. And then when it's become too shallow, they fall. I have to find. I had a very nice picture. It's not my computer. So that's a picture from some coast in Peru. So that's, you see that when, so this you can see in our product. When you look at far away, you will see that there are, he's very shallow. So you really see the patterns everywhere. But if you go to Arpoador, it becomes quite deep. So deep in the ocean, there is no pattern of waves just coming one after another. It will be very disordered. And whenever it comes to the shallow part, it forms the soliton-like solution. So every solution, every wave here is a more or less is a cosine hyperbolic in the power -2, with a more or less constant between each other. So this is a pattern that forms, and whenever it comes to become very nonlinear, it falls. So that's what happens, and you see that we can explain it essentially without even touching the equations for the fluid dynamics. So just from very general symmetry considerations. That's it. So let's. So now you have Carnaval. A good time to repeat. So repeat all this material, and then who wants to pass the exam? The exam is February 28th, 10 o'clock, here. It's 232, right? 232. So, fevereiro 28, 10 horas de manhã, 232. So you just come, don't worry, just look at all the material. You can bring all the notes. So this is, I don't give any limitation, and just count for several hours that maybe you can spend here, and then when we finalize.